Compiler construction 5. So I just made this video and I was uploading it and I was like on autopilot and I accidentally dragged it to the trash after I had started uploading it, and then the uploading got messed up, so I have to redo it. But I already wrote down everything, and so I don't really want to write it again. So I'll do my best to point out anything, but this will be slightly faster because I've just did it, so my mind will be more clear and I can just point at things, but hopefully it'll be a good experience. So recall that last time we finished the final connection of going from the R language all the way to X, and we can really run programs. However, our compiler is kind of bad, and the reason it's kind of bad is because it completely ignores the fact that there are registers on the machine, and it just uses only the stack. Now, the stack is very, very large. We say that the stack is vast, but it's slow. What we mean by slow is that when you access the stack, you're accessing memory. Since you're accessing memory, that means that it's beyond the edge of the lowest level of the cache hierarchy, which are the registers. Now, it turns out that for our programs, it's very unlikely that you're going to be able to write a program where you'll actually observe the performance difference between writing the program, between the compiler using registers and not, just because our programs are so small and they run quickly. But in principle, we should make a good compiler. So registers, in contrast to the stack, are extremely few, and they're like less than 16 of them. Now, you might think that they're exactly 16, but there's less than 16 because we can't use RAX because it's the return register, and we can't use RBP because it's the base pointer. We can't use RSP because it's the stack pointer. So we really only have 13 registers. So what we're going to do is, in our assign homes function that takes the x variables to x with no variables, we're going to just change that one function. We're going to change that one function so it's going to do a better job at doing register allocation. And to help explain how it works, we're going to look at one simple program and show what that one program would do. So here's this program. So we're going to say that v is 1, w is 46, x is v plus 7, y is 4 plus x, and z is x plus w, and then we're going to return the addition of x and minus y. This is very similar to the RCO program. If we were to convert this to RCO, there would be one more step, which is that there would be a temporary variable for y and a temporary variable for x plus that, and that's what we would return. So let's look at this variable, this program changed into the X language. So that's what we got right here. So going from the top, our program started with let v equals 1, so we're going to move 1 into v. Now notice that I have an exclamation point here. This is just kind of like a typographical hint to tell me that this is a variable, to help me remember that this is like the version of the X language before I've removed variables. And the next thing we got w equals 46, so we say move q 46w. Then we have let x equals v plus 7, so we move v, that's the left-hand side, into x. Then we add q 7 and x. Then we got y equals 4 plus x, so we move x into y and then add 4 and y. Then we have let z equals x plus w, so we move x to z and then add w and z. Then we have minus y, so we move y into t, which is just a temporary variable, and then we negate it. Then what we do is we're going to return the addition of z plus t. So we move z into RAX, and then we add t to that, and that's our final answer, RAX. And let me just adjust something real fast. RAX and RAX. Okay. So this assembly program right here, we want to analyze this program and figure out which variables are needed at every given point in time. We call that the live set, the set of variables that are active. Now, you and I can look at this and kind of just eyeball it. So for instance, we can say something like, aha, look, when at this point of the program, we start using v, and then v is only needed in these 3 lines. And then like over here, we use it here and then we consume it there, so it's needed in these ones. Then like w is assigned here and then it's needed until there. X is assigned here and we last read it there. Y is assigned here and we last read it there. Z is assigned here and it's last needed there. T, and then RAX and RAX. So you can kind of look through the program and using your giant human brain, figure out when variables are needed. Now, what we could do is make a really simple register allocator that just started at the top of the program and just went down the program, and every time it saw a variable, it said, oh, okay, is there a free register? And if so, use it. So like, the first variable we saw would get 1 register, and then the next one, the next one, the next one. The problem with this, though, is that it ignores that information about when variables are actually needed. And doing so would basically make it so that, like, if your program started and it had a whole bunch of temporary variables, but then it never needed them again after that, like, you would never realize that. You'd never keep using registers. So essentially what we're doing is we need to do something that's very similar to memory allocation, except that rather than allocating memory in like a big giant, 8 gigabyte heap, instead what we're doing is we're allocating memory when there are only 13 spots. There are literally 13 spots. And we have the advantage of knowing everything that's going to happen to the memory. So we know that our program is this particular thing, so we can analyze and figure out, okay, well, at this point in the program, we can use register 2, and this one we'll use register 3, and then this variable right here, it's not needed anymore, so we can like free it and then use that same spot somewhere else. So that's what we're going to build up to. Now, what we're going to do is we're going to codify that information about when variables are needed into what is called the live after set. The live after set is written right here, and we actually start at the bottom when we think about the live after. When the program is over, the only thing that we care about is RAX, because that's where the answer goes. So we write RAX down here at the bottom. Now, this live after right here and this line of the program are going to determine what the previous live after is. So for instance, we know that we care about RAX. Then we look at this program, we say this program reads T. So that means that just before this, we need to know T and RAX. Then we look at this line of the program, we see that, aha, it writes to RAX and it reads Z. So let's remove RAX and add Z. Now we get T and Z. Over here, this one writes to T and reads it, so we remove it and then add it back again, and that gives us TZ. This one writes to T and reads Y, so we remove the T, add the Y. This one reads W and writes to Z, so we remove Z and add W. Oh, but it actually also reads from Z, so we add W, add Z, and remove Z. So we go back to here. This one right here, it writes to Z and reads from X, so we remove the Z and add the X. This one right here, we read from Y and write to it, so we add and remove it. This one we write to Y and read X, so we remove Y and then add X, and we get X, W. This one reads and writes X, so it stays the same. This one writes X, so we remove that, and then reads from V, so we remove the X and we add the V, and we get VW. This one right here writes to W, so we just get V. And this one writes to V, so then we get the empty set, which I've written here on the side as empty. It's with an arrow pointing up to above there. So what this does is this is what's called a bottom-up algorithm, where it starts at the bottom of the program and works backwards to figure out which variables are needed. We can codify this algorithm in the following way. We can say that suppose that we have a list of instructions, I0 to IN. Then what we'll do is we'll say that the live after of the kth instruction is empty, or %RAX, if k is equal to n. Or, if it's not equal to n, then it will be whatever live before is for k plus 1. Then live before of k is equal to the live after of k, where we have subtracted out the things that are written in step k and added in the things that are read. W is a function that takes an instruction and returns the set of variables and registers that we wrote, and R takes an instruction and returns the set of variables and registers that we read. So for instance, if we imagine writing this, like, what gets written in a popq instruction? Well, it's whatever variables are mentioned in the argument, where mention is a function that takes an argument and returns a set of registers. So for instance, when you mention a register, you just get that register. When you mention a variable, you just get the variable. If you mention a number, then you get nothing, and so on. And what gets read by a pop instruction? Well, nothing gets read. What gets written by a push? Nothing, but what gets read by a push? The things that are mentioned by the argument. If we look at a negation, the things that are written are what's mentioned, and the things that are read are also what's mentioned. If we look at what's written by an add, we write to the destination, and we read from the source and the destination. Think about a move. What gets written in a move? Only the destination, and what gets read? Only the source. Now, if we take an instruction like the 7th one, which was move bang x bang z, the live after for it, the thing that was written on that line, was w, y, z. So what gets written in this? Z does. What gets read? X. So we take w, y, z, subtract away the z, add the x, and we get x, y, x, w, y. So if we go back, we can see that right here we indeed have x, w, y, just like we saw. So doing this gives us the list of live afters. Now, what we need to do with this this sequence of live after sets is we need to look at it and figure out when two variables conflict with one another. Now, what do we mean conflict with one another? What we do is we call this interference. Let me move this down. Interference is when we need two variables at the same time. So we can think of this as being a graph. So the graph is a graph is always a list of vertices and a list of edges. A set of vertices and a set of edges. So the vertices would be the variables and the registers in our program, and the edges we call I. And we say that x is related by I to y if and only if there exists a k where the live after set of k includes x and y. And we actually are going to talk about two different graphs that are just different sets of edges for the same vertices. And the first one is the interference graph, and the other one is something that we're called the move graph. So I'll talk about that in a moment when we talk about how to find these things. So notice that what we could do is we could make like an n-squared algorithm that just iterated through every variable and then every other variable, and then search through all of the different sequences, all of the different live after sets, and just saw whether or not they were there. So we could actually populate this table. You could like make an adjacency matrix for all of the variables and registers, and then figure out what the value of any given point was by just iterating through all of the instructions. That cubic algorithm for doing that is too expensive, and we're not going to do that. Instead, there's a really simple linear algorithm that works. The way that the linear algorithm works is that we walk through each instruction and we look at what that instruction does. And then we look at that instruction and its live after set. And here's what we do. So suppose that we're looking at instruction K, and that instruction is like an add. Then if it's an add, it has a source and a destination. So what we're going to do is for all the variables that are mentioned in the live after of this instruction, we're going to add dv, that's the destination, and v to I, except for when v is equal to d. The idea here is that if d is live after this point, then that means that it's being assigned by this. So it doesn't really interfere with those things because like it may yeah, it may be needed. And if it's a move, we're going to look through everything inside of the live after set, and we're going to add dv to I, except for when v equals d or v equals s. In this move thing right here, this is going to be where something interesting happens, because what we're going to do is we're going to say that two things are not going to interfere with one another if they don't, sorry, if they, it's not that they don't interfere with one another. It's that we're going to also keep track of the fact that they're related to move. So what we're also going to do is we're also going to add SD to M. This is this M graph that I talked about before, the move graph. And what this is going to do is it's going to record the fact that these two registers are related to one another because there could be a move. And what we're going to look for when we start doing register allocation is we're going to look for an opportunity to assign S and D to be the same register. If we can do that, then it'll make it so that we ultimately have fewer registers needed in our program, which is nice. Finally, if the instruction that we get is something that treats a certain register as special, then for all of those registers that are special, we're going to add RV to I for all of the variables inside of the live after set. Now, what treats something as special? So right now, the only things that treat things as special are like push queue, pop queue, return queue, call queue, things like that. Like those things treat the stack special because they treat RSP special. And then the other thing that treats things special is a call queue, because a call queue is going to treat all caller saved registers as special. So if you don't remember from your assembly programming, courses or whatever, or days, when you call a function, we can imagine a world where when you call a function, it is in control of everything. Or you can imagine a version where when you call a function, it is responsible for keeping everything exactly the way it was before. But that's not really the way that it works. Instead, we take all of the registers in a machine and we split them into two sets. The ones that are assumed to be in control by the caller, and the ones that are assumed to be in control by the callee. That's the one getting called. And the caller has to save the registers that the callee owns. So they're called the caller saves registers. And the callee saves registers, they're the ones that the caller owns, so they don't have to keep track of them. So essentially what a call queue does is a call queue, you're gonna imagine that all the caller saved registers, the ones that are owned by the callee, have to be treated specially because you assume that they get written. And so in that case, we're gonna mark all of those as interfering with all of the variables that are live at this point of the program. Okay, now suppose that we do all that, we're going to end up with the following graph. Now, when you look at this graph, scroll back to this page in the notes, 5.2, and you're going to look through this as I talk about this. Okay, so let me just open it up so I can see also. Okay, so because in the third line we move v into we move v into x. Hold on, am I looking at the right thing? Because we move v into x. Okay, let me switch back and forth between these. So because right here we move v into x, we're going to look at all of these variables right here, except for the destination, which is x. And then we're going to add v mapping to there, to w. So we're going to make it so that that these variables, the destination x, conflicts with all of these things. So we're going to add an edge from x to w, which we see right here, x to w. That line also starts off with, sorry, the first, let me start at the, I started at the third instruction for some reason, let me go back to the first. So the first instruction is move 1 into V. So that means that we're going to look at the live set, which is just V, and add a conflict there, but there aren't any. The second one is the W. So we're moving into W, and the set contains V and W, so we're going to add an edge from V to W. The third one makes an edge from W to X. And then we're going to add edges. Yeah, I need to open up. I need to open this up differently so I can see it. Just hold on 1 second. Okay. All right. Now the third line is an add queue. And the add queue, the destination is X, and the live set is W and X. So there's already a line, there's already an edge from W to X, so we don't need to do anything. The next one is a move queue, where the destination is Y, and the live set contains X and W, so we want Y to conflict with W and Y to conflict with X. After that, we have an add queue, and the destination is Y, and the sets are the same, so we'll skip that one. And then we have, oh, you know what, and I forgot the move. So on the third line, we saw a move from V to X, so we added that line. And on the fifth line, we saw a move from X to Y, so we added this edge. Okay, now, going back to the add WZ. So that one, the destination is Z, and the live set contains Y, so we add an edge from Y to Z. You know what, I think I skipped the previous one, the X to Z. So in that one, the destination was Z, and the live set contained W and Z. So we have an edge from W to Z and from Z to Y, and we had an edge from Z to X. Now we get to the move Q Y T. So that one associates a move edge with Y and T, and makes a conflict edge between T and Z right here. Then we have the negate, which is like an add. So the T is the destination. So the destination there is T, but we already have an edge from T and Z. And then we have a move Q of Z to RAX, and the live set is T, so we make a conflict edge between T and RAX. And I guess we can also add a move edge from Z to RAX because we move Z into RAX. And then we have the add edge where the destination is RAX, and the live after set is just RAX, so nothing changes there. So this right here is the interface graph that we construct and the move graph that we construct. Okay, so now we have constructed all the information that we're going to use for figuring out what the registers are going to be. Notice that constructing the live after set is a bottom-up algorithm because we have to start at the back and work our way backwards computing the live after sets. And then it turns out that doing the computing the interference graph, you can think of it as a top-down algorithm, but actually you can also think of it as a bottom-up algorithm because it's more like it's a local algorithm. We look at every single instruction individually and then look at its live after set, and we use that to consider things that need to get added to I. So you can actually make it so that you compute the I and the M while you're doing the live after, and you don't even need to like save the live afters anywhere. You just have it be like an intermediate part of your computation. But now what do we even do with these graphs I and M? That's what we'll talk about next time, but I'll give you kind of a clue to the basic idea. The basic idea is we're going to say something like, well, given that W right here is conflicting with V, Y, and Z, that means that they can't share those four things. Sorry, W can't have the same register as V, the same register as Y, or the same register as Z. And so essentially what we're going to do is we're going to look at this graph And we're going to try to start assigning registers to values. Sorry, we're going to start assigning registers to variables. And then we can assign a register to a variable as long as the things that it's connected to are not already assigned to that register. Well, you may be familiar with graph problems and recognize that what I just described is the graph coloring algorithm, the graph coloring problem. So the graph coloring problem essentially says that if you have a graph, how can you label the edges, label the nodes in a way that two nodes never share the same color? In this case, color is going to mean register. All right, so we'll talk about that next time. And yeah, so see you at the next class.